field. Covenant. Covenant.
Hello, sir.
What is a potential field?
Okay, a potential field method is a method that measure naturally occurring field for main Laplace's equation.
Okay. So what is Laplace's equation?
So Laplace's equation is an equation that deals with the what's it called the magnetic field and gravity field.
So what does he say? What does the equation say? Equation of a straight line say y is equal to mx plus c. So what does Laplace equation says? So you said potential field, the sample of potential field is magnetics and gravity field. So it is this field when you measure this field in geophysics, we call them methods. So in potential field method, we have magnetic method, we have gravity method, and some other ones. So we want to look at gravity and magnetics methods, which are geophysical method that measures variation in naturally occurring gravity and magnetic field. So that is what is. So we are just doing introduction of that. Okay, let me remove this. So I think I've taught you before. I taught you last semester. So
Yes,
what
sir.
is gravity? So gravity is the branch of geophysics that deals with the measurement of the gravitational field of the Earth. You can also call it the gravity field. You can also call it gravimetry if you like. But we measure the gravitational, variation in the gravitational field. I'm going to take you through how the gravity occurs. What does the word gravity means? Gravity is a force of attraction between bodies that have mass. The way you are seated, if you are seated close to one another, we are attracting one another. But the reason why you are not being moved or you are not seeing the effect of the attractions, as in when you have two magnets close to one another, is because of our rigidity. We are rigid, so that is why, and we are massive. But the force is not that big, so that is why we are not drawing towards one another the way magnet will draw a metal. So gravity is a force of attraction that exists between two bodies that have mass. So the word gravity comes from the Latin word gravis, meaning weight or heavy. So when you have two things that are massive, they attract one another. You might not see them moving towards one another, but the example of attraction that you can see between two bodies is what we call tide. If you have been to the beach before, you will see the way ocean water is rising up. The reason why the ocean water is rising up and falling is because the sun, which is another planetary body, and the earth are attracting one another. Because the mountains are rigid, you are not seeing the effect of the pull. But because water is not rigid, when the moon pulls the earth, when the moon attracts the earth, the water bodies will respond to it, and the water will lift up, as in the case of tide. So that is an example of manifestation of gravitational attraction between two bodies, which is, in this case, which are the moon and the earth. The natural force, gravity is the natural force that tends to cause physical things to move towards each other. It is then force. It is still the same force that causes things to fall. If you throw something up, the earth will pull it down. That is why it's falling. The earth is pull. If you throw or if you jump up, you come down again because the earth is pulling you down. Differences in rock density produce small changes in the earth gravity field that can What is the formula for calculating density? What is the formula for calculating density?
Mass over volume.
Mass over volume. You can see now that since we have been talking about gravity, we said it is about massive body. So you can see that if you want to calculate your mass, the mass will be equal to density multiplied by volume. So variation in density of materials will determine or will affect variation in the mass of that particular material. So if a particular material is dense and there is another version of it that is not dense, if the two of them are of the same volume, which one will be more massive? Is it the one that is dense or the one that is less dense? Which one will be more massive? The same material, the same volume, but different density. Will the mass be the same? If no, which one will be higher, which one will be lower? Adedeji Ayomide. Adedeji Ayomide. Shasikwe. Are you guys there? Shasikwe.
Sir?
I say if you have two materials, one
Yes, sir.
material,
Yes, sir.
there is a portion of it that is denser than the other, though the two of them are of the same volume. Will the mass be the same or they be different?
Of denser material, sir. I feel the mass will be different, sir.
Why do you feel so?
Eh, because I think mass is directly proportional to, inversely proportional to the density of the material, sir.
No, they are directly proportional. It's directly proportional. It's not inversely. As
Okay, sir. Okay,
density
sir.
of yes, as density of a material, as density of a material increases, the mass also increases.
All right, noted, sir.
Okay, good. So density is equal to mass over volume. If you make mass the subject of the formula, mass will be equal to density times volume. If the volume is constant, the mass is directly proportional to density. Okay. So in geophysics, by measuring the distribution of gravity and its change with time, it is possible to know what we are just saying on this slide is that we are talking about applications, usefulness, relevance of gravity field or measurement of gravity field. By measuring the gravity field, you can determine the shape and size of the earth. Or we can put it in another way. Those people who determine the shape and size of the earth used measurement of gravitational field to determine that. So what is the shape of the earth?
Geoid.
Is that what?
Geoid, sir.
Okay. Okay. Whatever you call it, the shape of the earth and the size were determined through measurement of variation in gravitational field. And what discipline does that? That discipline is referred to as geodesy. Is that okay?
Yes, sir. Yes, sir.
So apart from in geodesy, we also use gravity in estimating underground construction. For instance, if there is a cavity in the subsurface, but on the surface, you don't know that there is cavity there. If you measure gravity across the area, the place where there is cavity and the portion where there is no cavity, will their density be the same? No response.
No, sir, their density will be different, sir.
So, and don't forget we have said density influence the mass. Mass determine the gravity. So since if you measure gravity field along that path where there is a cavity, the location where there is a cavity, we have less gravity measurement because the underground is not dense because there is mass deficiency in the subsurface. So that is part of geophysics. You can use it, measurement of gravity to estimate underground construction, to study the seismic and volcanic activities. Can anybody who is interested, I want to dash out 5 marks, and I want somebody who can tell me, the beneficiary will be the person who can link volcanic activity to measurement of gravity. Somebody who can tell us why is it possible that you can use measurement of distribution of gravity to monitor volcanic activities. Anybody with 5 marks, just once you get it, tell me your name, your matric number. You have 5 marks waiting for you already. So you just need to fight against 10 or 95 marks in the exam. Anybody? You guys do not want 5 marks?
Morning, sir.
Yes, what's
Morning,
your
sir.
name?
Demilade, sir.
Okay, Demilade, okay. Relationship between gravity and volcanic activities.
So, sir, during volcanic activities and all, it involves the movement of magma underground and
Yes.
extreme pressure through rocks. So that can cause gravitational anomalies since mass gets concentrated in one spot before eruption, of course.
You have geophysical sense, and that is the way geophysics, you have accumulation of magma in a particular area prior to eruption. Is either the magma is less dense than the surrounding or is more dense than the surrounding, will not be of the same density with the surrounding.
Yes, sir.
And as a result of that, what about seismic activities? Demilade, how can you link gravity, measurement of gravity, and seismicity? Do you know what seismicity is, Demilade?
Okay. Yes,
Do you
sir.
know what is seismicity?
It refers to the frequency and occurrence of earthquakes in a particular region over time, sir.
Okay, let just call it earthquake. So how do you link earthquake occurrence to gravity? How come that you can, by measuring variation in gravitational field in an area, you can determine the preponderance of that area to earthquake?
Okay, so since earthquakes are simply, let's say it's like the splitting of the earth or the joining. Earthquake is the product of forces acting within the subsurface, which causes the ground or rocks around it to either like to compress or break, causing fault lines. So you can measure, since these forces, since these rocks also have mass and volume, you can also measure the gravity of them and their changes or gravitational anomalies during their occurrence.
Very good attempt. How does seismicity causes differential density? How will occurrence of seismicity or earthquake make density to vary in an area? That's just what I want to hear now. Or to make mass vary in an area.
Okay, very good. I would say that the rocks could either break apart, reducing their mass, breaking them into different pieces, also which causes cracks to appear on the surface, or the force between these rocks could push together, forming an uplift or
So, so, so,
anything.
so very beautiful attempt, Demilade. I'm proud of you. When those rock come, anybody want to say something?
I wanted to add to that, sir.
Okay. What's your name?
To what Demi said. My
Huh?
name is David.
David what?
My name is David, sir.
Okay, David.
Wow.
I'm listening to you.
Uh,
I'm
okay.
listening to you,
So
David.
what you were just trying to say was earthquake causes redistribution of mass. So
No, no, no,
when
no.
mass has been
David,
redistributed.
David, listen to me. Before you can say it causes, you see, for somebody to have good geophysical sense, you must be able to link it from the beginning. How does it cause distribution, or what do you call it, of density or mass? How does it cause it? That is the first thing I want to hear.
Okay,
What
sir.
happened?
When there's
Okay,
a stress in the fault line. Okay. When there's a stress and earthquake is produced, um, the mass of the how do I put this now? The mass of that certain area has been redistributed, leading to altering of the gravitational force around that side,
okay.
creating of cavities. One.
Okay. Let's look at it this way. I really like I'm proud of you guys that even in 100 level you are understanding this concept. There are some of those guys that are ahead of you in final year that do not quite have this depth of understanding you have about this thing. I really appreciate that, and kudos to you guys. Now, for seismicity or earthquake to occur, there is a process. If you have fault line, the rock are trying to slide against one another along the fault line. But due to friction, it will not slide easily. It will be pressing against one another. Due to friction, it will not move. As it's doing that, the rock are compressing. The compression will lead to what? Increase in density of the rocks in that area. So even prior to earthquake, before earthquake occurs, as you are measuring gravity, you are seeing gravitational response increasing along that line, especially if there have been a fault in that area. So you know that since gravity is increasing along this fault line, it must have meant that there is compression along the fault line. So as the rock are trying to slide past one another, stress will be building up. The rocks will be compressing. So when the stress is now released, that the stress is able to overcome the friction along the fault. The shaking that results from that is what is called the earthquake. So it is possible for you to monitor earthquake through measurement of gravity. The same thing, volcanic activities. The magma will not just wake up one day and erupt. No. It will have been building up in the chamber. And then you can measure that, which can either result to gravity deficiency or increase in gravity. So you can also use gravity to investigate viscosity and elasticity of the earth, which is similar to what we just discussed. Elasticity is related to seismicity, whereas viscosity is related to volcanic activities. So you can use it to find hydrocarbon. We'll talk about that at the end of the class. So the theoretical background, like we have said, gravity, the gravitational law of attraction was discovered by Isaac Newton in 1685, and it formed the basis of the gravity method. Like we have said, we said gravity is an attraction or attractive force between two mass, at least a pair of massive objects. It might be rocks, it might be planets. So the Newton law is referred to as universal mutual gravitation. Gravity works everywhere in the universe, and it's one of the major physical phenomenon that is measured in astronomy and so on and so forth. So it works everywhere, not just on Earth. We say it is mutual because gravity works between pairs of objects. So the force of gravity depends on two important factors. Number one is mass. Gravity works with massive materials that has mass. And the mass and the attraction between these two masses is dependent on the distance between the masses. If the two masses are close to one another, the force of attraction between them will be high. If they are farther apart, the distance is large, then the force of gravity will be low. So mass and weight. Mass and weight in popular language, or in for a layman, mass and weight might refer to the same thing. But in science, in physics, weight is a product of mass and gravity. Where there is no gravity, weight and mass are equal. But for it to be referred to as weight, a mass must be experiencing gravity. A gravityless mass cannot be referred to as weight. But the reason why people commonly say mass and weight are the same thing is because we are all under the influence of gravity. So you can easily equate your mass to your weight. So mass is a measure of how much materials are in an object. Why is exerted on that material. I've said. So for its mass is constant. Can you hear me?
Yes, sir, but your screen has stopped sharing, sir.
Oh, okay. Let me where is the guy now? So can you see the screen now?
Yes, sir.
Yes, sir.
Okay. So now I said the theory, the concept, or the gravity method of geophysics have their foundation, their basis. The gravity method is founded on two laws, both derived by Isaac Newton. And those two laws were extensively discussed or described in a journal referred to as Philosophy Naturalis Principia Mathematica, published in 1967. The two laws are: one, the universal law of gravitation. Two is the second law of motion. Can somebody remind us what second law of motion says?
As the rate of change in momentum is directly proportional to
Is directly proportional to what?
the applied force.
So, good. It is that force we are interested in. That force, what is the formula for that force?
Mass times acceleration.
Mass times acceleration. Now, the universal law of gravitation, what does it say? What does it say?
It says that the force of attraction between two bodies is directly proportional to the mass of the
So,
body and inversely proportional to the square of the distance between.
beautiful. You can see in the universal law of gravitation, we have force. In the second law of motion, we have the force. So we are equating the two forces together. So that is why the two laws, both derived by Isaac Newton, form the basis. So as we are going to see, the unit of, okay, we'll talk about that. We'll talk about the unit later. Let me leave that one for now. So now, let's now look at the laws proper now. One, we said Newton's law described this is the formula, Newton gravitational law of gravitation that we just talked about. That force is equal to gravitational constant, mass 1, mass 2, that are separated by distance r. So you can see that, like we have said earlier, is directly proportional to hold on. Hello. Good afternoon. Hello, I can hear you. Good afternoon. So sorry for the interruption. So I was saying that you can see from this formula that the attraction between two masses is a function of the mass, how big the masses are. From this equation now, you can see that F is directly proportional to the masses and inversely proportional to the square of the distance between them. So, so That is for that. But for second law of motion, we have said F that that is causing the momentum is equal to mass times the acceleration. So you can see we can equate these two together. We can equate the two together. So if the acceleration this time around is acceleration due to gravity, then, and this is also this force so F over M will be equal to G and it will be equal to this, where capital letter G is the acceleration due to gravity. So the SI unit of G is what you can see here in meters, meter cube per kilogram per second square. So this is how, so what we now do is that it is this G that your equipment is, or that you measure in geophysics, variation in that G. And you can see that G is a function of R and it's a function of M. So this is how gravity attracts everything, how the earth attracts everything under its influence. What you see here, what you see on this slide is the gravitational field. You can see the earth. The force is acting towards the center of the earth. This shows the gravitational field of the earth. We are on the surface like this. And the reason why we are still on the surface, even when you jump up, you come down, is because the earth is attracting you down here. That is why the force, the line of force, are directed towards the center of the earth. So another thing you will see is that the first thing you will see is that the force are unidirectional. They are directed towards the center of the earth. Number two is that we see that the gravitational field is symmetric. What is the meaning of the word symmetric? When something is symmetric, what does it mean?
They are the same in all directions.
Good. So, and they have approximately equal magnitude. That is, wherever you are on the surface of the earth, apart from the little differences at the equator and the pole, the value is the same. And there are three things we have said here about the gravitational field of the earth. One, we said they are symmetric. Number two, we said they are approximately equal in magnitude. Number three, we said the field is directed towards the center of the earth. As you are going to see by the time we get to magnetic method, you will see that it's not the same. So you can see, this is how it occurs. You can see mass A and mass B separated by this distance. So the force between them is expressed by this. So again, you can see M1, M2. That's from Newton's law of universal gravitation. It gives us that if this is the earth, which is M2, anything M1 is being drawn, attracted by M2. The one that is more massive will be drawing the one that is less massive towards itself. So this is pictorial representation of Newton's law of universal gravitation. This represents Newton's second law of motion. The acceleration with which, if you have this thing falling towards the earth, falling with acceleration A, and the mass of the object is m. So the force of attraction between them is this. So if we equate A to G, like I said, then of a body depends on only the mass of attracting body and the distance. So you can now say G, if you make G the subject of the formula, even from like we have done earlier on, that will not be repeating it here. So you get G, small letter G is equal to GM over R squared for a perfectly spherical earth. So this is we are still talking about the same thing here. So as you are going to see here, to measure gravity, what you actually measure is that you are measuring variation in acceleration of gravity. G, that is what we measure in gravity method. So when making measurement of the earth gravity, okay, let me ask you a question and let me see how you will respond to it. We have been talking about gravity, and I now say what to measure when you are doing gravity method or gravity studies. What to measure is acceleration due to gravity. What is the unit of acceleration due to gravity?
Meter per second square.
Okay, what is acceleration?
Acceleration is the rate of change in velocity.
In velocity. Can somebody now, from what I've said, how is acceleration linked to gravity?
There
You
is
get
a
my
force of
question?
attraction. Yes, sir. Yes, sir.
Yeah, okay.
I said
Is that
that
Demilade?
no, this is Michael.
Michael, okay.
There is a force of attraction between two bodies. From Newton's
Beautiful.
second law, we know that force will cause acceleration of an object. So if there's
Okay.
gravitational force will cause gravitational acceleration. That's why we say
So,
acceleration due to gravity.
so the measurement of variation in that gravity will reflect the force of attraction. Is that not so? Because the higher the acceleration, the higher the force of attraction. Is that not so?
Yes, sir.
So
Yes, sir.
that is why measurement of gravity is done by measuring variation in acceleration due to gravity. So that's what. So the gravitational acceleration is the time rate of change of a body speed under the influence of gravitational force. Now, let me now ask you, how can I ask you at this point? But when I want to measure acceleration due to gravity, don't let me ask you the question now because you might not understand. So if you look at what we have here again, you have two body. I mean, you have this is the earth, and you have a mass. The earth is attracting it. The acceleration due to gravity will be g. Now, you now have a situation here. This is the earth, and this is a feather, and this is a big cupboard. Assuming that wind resistance or air resistance is 0, there is no wind, there is no resistance. Both the feather and the cupboard will get to the earth surface at the same time, because the earth is attracting them with the same force. So the mass m of the earth with radius r to the Earth center determine the gravitational acceleration of object above the Earth. So the acceleration is the same for both the feather and the cupboard, regardless of the mass of the object. The Earth will draw them with the same, because as you can see from here, acceleration due to gravity depend on what? What are the parameters that determines acceleration due to gravity here?
Mass and radius, sir.
Mass and radius. That radius is the radial distance from the center of the Earth to that body on the surface of the Earth or higher above the atmosphere. So you can see the acceleration due to gravity does not depend on the mass of that material that is within the that is on the surface of the Earth. Is that one very clear?
Yes, sir.
So it does not depend. It does not depend on the mass. So that is why a feather and a cupboard, when wind resistance is 0, when there is no wind, there is no air resistance or what have you, the two of them will fall to the Earth at the same time. The cupboard will not reach the Earth before the feather. Why? Because the acceleration of that body under the influence of the Earth gravitational field does not depend from that equation that you have seen, does not depend on the mass of the object. It only depends on the mass of the Earth, which is constant, and then distance to the center of their radius. So if the two objects are on the surface of the Earth, the radius is also the same, which implies that the acceleration due to gravity is going to be the same for the two objects regardless. But if you now have one that is closer to the surface of the Earth and you have one that is far above the surface of the Earth, the radius is now different. In this situation, the one with smaller r will have higher acceleration due to gravity than the one that has very large r. So theoretically, what it means is that acceleration should become constant over the Earth. Since acceleration is determined by the mass of the Earth, which is constant everywhere. Number two is that the radius of the Earth is constant. Provided that the Earth is perfectly spherical. So that is what I'm now saying here, is that theoretically, acceleration due to gravity should be the same over the Earth. But in reality, gravity varies from place to place on the surface of the Earth. Why? Because of 3 to 4 reasons, which we are going to mention. Okay, we mentioned that when we get there. So now you will see from here that the Earth is not perfectly spherical. There is mountain, like this one represents mountain on the surface of the Earth. These are valley, sea level. You have valley, mountains, and what have you. So in actual sense, the radius of the Earth is not the same all over. Coming back to that. Theoretical gravity. The average value of gravity for a given latitude is approximated by International Association of Geodesy, IAG, in 1967. What do we mean by theoretical gravity? This is very important. The theoretical value of gravity is a value of gravity at any point on the surface of the Earth. You know, we have said, if the Earth is perfectly spherical, but the Earth is not perfectly spherical. But what scientists now did was that, okay, let us assume that the Earth is perfectly spherical. And then let's assume that the Earth is homogeneous. What is the meaning of homogeneous?
Made from the same material.
Material. Those are the two major assumptions that scientists made to calculate theoretical gravity. And what is that theoretical gravity? Since the Earth is perfect, they are calculating what will be the gravitational response of the Earth when the Earth is perfectly spherical, which is not, and when the Earth is homogeneous, is made of the same rock, of the same mineral. But in actual fact, is the Earth perfectly homogeneous?
No, sir.
Can you tell me why it's not homogeneous? Can you cite example or instances or reasons why you think the Earth is not homogeneous?
Because there are different minerals and different rocks on the earth
Rock
of
types.
different density. So
Thank you very
rock
much.
types, so they'll contribute to.
So we should make the assumption to fail. Is that okay? Hello, are you there?
Yes, sir. Yes, sir.
Yes, sir.
Okay, good. The second one, we say the Earth is a perfect sphere. Is the Earth really perfectly spherical?
No,
No, sir.
No response. So
no, sir.
essentially, the Earth is not perfectly spherical. The Earth bulges at the equator and it flattens at the poles. But to make calculation easy, they calculated the gravitational response of a homogeneous Earth and a perfectly spherical Earth. And another thing is that they assume that the topography of the Earth is topographyless. That is, the Earth is of the same elevation all through. And this is the formula they came up with. At the equator, theoretical gravity of the Earth, where Gn is the normal gravity. Normal gravity is another word for theoretical gravity. Can somebody tell me why do we call it theoretical?
Because it is not the true gravity.
It's
True
not
It's
the
just
gravity of
taken
the earth.
practical.
because of assumption.
Beautiful. That is why it is theoretical. So the theoretical gravity is also referred to as the normal gravity, which is denoted by G subscription N. So normal gravity is the gravitational acceleration expected for a rotating ellipsoidal Earth without any geology complications. What we mean by any geology complication is that it is homogeneous. It is not heterogeneous. And no surface features. No surface features means it is perfectly spherical. There are no mountains and there are no valleys. Hence, that is why it is theoretical. But in practical, the Earth is not without geological complication. It has geological complication, different rocks, different mineral, different structures. The Earth has surface features. There are mountains, there are valleys. That's why we call it normal gravity. But this normal gravity is the gravity of the Earth, calculated for homogeneous, perfectly spherical Earth. This phi is the latitude. So, and what it just means is that, what this normal gravity just means is that if you know the latitude of a particular location on the surface of the Earth, put the value of the latitude in the air, in the phi, and you will get the gravitational response for that particular location. I repeat, the essence of theoretical gravity or normal gravity is that you are able to calculate gravity response, the value of gravity at a particular location, provided you know the latitude of that location. That is theoretical gravity or normal gravity. Later, I don't know whether here or when you are doing gravity, I'm going to tell you the significance of that. Okay, let me tell you now the importance of that. So we call this formula, we call it International Gravity Formula, IGF, International Gravity Formula, derived by the International Association of Geodesy in 1967. Now, you know, this value is for homogeneous Earth. But in the crust, very close to the surface of the Earth is not homogeneous. So once you measure the gravity of the Earth using an equipment on the surface of the Earth, that is, in practice, you measure it. You can now calculate the normal gravity for that location and subtract it from the one you measure. So what is the anomaly, the gravity anomaly. Can you hear me?
Yes, sir, we can now.
Yes, sir.
Yes, sir.
Okay, good. So that is, if you have any question along the way, kindly let me know. For instance, we are here now. How many are you in your class?
Like 40.
Like 40.
47.
Okay, let's just say 50. I wouldn't know. The geology student, are they offering this course?
No.
No, sir.
I wouldn't know whether we are going to give you German questions or it's going to be theory. Which one do you guys prefer for the exam?
Theory, sir. Theory, sir.
Theory or the German? No, if German question, you better come and fill the spaces. So we'll talk about that later. For instance, typical examination questions from this slide. Number one, you see, why is the international gravity formula referred to as theoretical gravity? Why? Anybody want to answer?
Because it is based on the assumption that the Earth is homogeneous and the Earth is a
Homogeneous.
perfect sphere, which it is not.
Beautiful response. We can say, what is normal gravity? The question, what is normal gravity?
Normal gravity is also theoretical gravity, which is the gravity measured when the Earth is homogeneous and when the Earth is a
Perfect sphere.
Okay. Another question is that, how will you bring down those two assumptions? Can you confront those two assumptions as not being completely correct? Can you confront those two assumptions?
Because the Earth is not perfectly spherical due to the topography of the Earth because of mountains and different sea levels. The Earth is not homogeneous.
No, that
That's the
no,
very
that is not
limit.
the sphere. The spherical is not a perfect sphere because the earth bulges at the equator and flattens at the pole. Is that okay?
Yes,
Yes,
Even if there are no mountains and valley, the earth is still not perfectly spherical because it bulges at the pole. Next slide, we are going to explain that. And then he said there are no geologic complications. What geologic complications are in the earth? This one assumed that there is no geologic complication. Can you tell me the geologic complications that this theoretical gravity overlooks?
there are some minerals, because of different minerals, which use different gravitational anomalies.
Beautiful. Different minerals, different rocks, and different structures. Where you have faults and the surrounding, the fault line or the fault zone will be less dense than the area where you do not have faults because the material along the fault zone are broken into pieces. So because the earth is not perfectly spherical, gravity increases, it is lowest at the equator, which is this value, milligar, and rises to 9 this value at the pole. What it just means that even if the earth is perfectly spherical, I mean, if the earth is homogeneous, the shape that make the radius to be longer by about 23 kilometers or thereabout at the equator than at the pole. Gravity generally increases from the equator to the pole. Why? Because R, don't forget that G is equal to capital letter GM over R square. The longer the R, the smaller the G, and the R is longer at the equator. So the value of gravity is smallest at the equator and highest at the pole. To the next. Our acceleration will have been the same. But let us look at the reasons why it is not the same. The main factor responsible. Can you hear me? Can you hear me?
yes, sir.
Good. The first reason, you can see, the blue is actually the shape of the earth. But you can see that it bulges at the equator and it flattens at the pole. But our assume that it is this red that goes this way, come out here. So the true shape of the earth is the blue, not the red. Now you can now say the radius of so the first thing is that the earth is an oblate period that is fatter at the equator and is thinner at the pole. We call it equatorial bulge. There is bulge at the equator. Because of the bulge, there are two things that this shape will cause. One, it will make equatorial radius, to be longer than the polar radius. Number two is that it makes more mass. Because this is longer, more mass accumulates at the equator than at the pole. The first reason why acceleration varies across the earth is one is the shape of the earth, which is an oblate spheroid. Oblate spheroid, not a perfect sphere. And for the oblate spheroid, there is bulges at the equator and the earth flattens at the pole, which make the equatorial radius to be longer than the polar radius. Number two, the longer distance implies that there are more material, more mass accumulated at the equator than at the pole. So there is an excess mass under the equator than the pole. Now, from the formula, G is equal to capital letter G, mass of the earth over r square. What will be the effect of excess mass at the equator? Will it make G to increase or G to reduce?
It will make G to increase.
Yes. You see, I don't like a word in my class. I just say it, even if you are wrong. It makes G to what?
Increase.
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 Yes, it will make G to increase. Now, that is for. What about the longer R? Will it make G to increase or decrease?
Make it to decrease.
Decrease.
Huh?
Decrease, sir.
It will decrease because it's the denominator.
Yes, sir.
Good. So you can now say the shape of the earth itself make G to increase at the equator, and at the same time, it make G to decrease. It make G to increase because of excess mass. It make G to reduce because of longer radius at the equator. Two things from the shape of the earth. The third thing is what we call centrifugal acceleration. All this while we have been silent about something. We have been silent about the rotation of the earth. The rotation of the earth causes centrifugal acceleration. And the centrifugal acceleration reduces gravitational attraction. What is centrifugal acceleration or centrifugal force?
So, sir, there is a centripetal force. Is it the same thing
Yes,
as centrifugal force?
they are
I said
opposite.
is
What is centripetal?
centripetal.
Okay, tell
Centripetal
me about
force is the
centripetal.
force that centripetal force is the force that pulls rotating body inwards to the center. Whereas from Newton's third law, we know that
That's not it.
centrifugal force.
What's your name?
Okay. Michael.
What's your name? It's not centripetal force.
Michael.
Yes, centripetal force does not pull something to the center. It pull it away. Something that want to push, something that you want to throw it away from the, there is a force directing that thing towards the center. That force is the centrifugal force. So the one that want to pull it away, yes. Let me explain to you. If you put some water in a bucket is filled with water, and you just put it and you begin to, you tie rope to it, and you begin to fling it around horizontally around you. The water will not pour away until you stop. It's the centrifugal force that is keeping it. Centripetal force want to throw it away. Is that okay?
Yes, sir.
So, as the body is rotating, there is the centrifugal acceleration. Sorry, what I said is not correct. The correct thing is centrifugal want to throw it away. What you said earlier on is correct. Yes. What you said earlier on is correct. Centrifugal want to throw it away. What you said earlier on, what you said is correct. Centrifugal want to throw it away. Centripetal is keeping it towards the center. Is that okay?
Yeah.
Is that okay, Michael?
Yes, sir. Thank you, sir.
Yes, what you said is correct. Centripetal tying it to the center is pulling it toward the center. But centrifugal want to throw it away. There is one centrifuge method in chemistry. Did you do it in primary and in secondary school or in your 100 level in chemistry? Separation of mixture using centrifuge.
Yes.
So how does it work? Anybody who can describe how separation of mixture using centrifuge, how it works?
I think he spins the test tube really fast in a circular motion, causing the mixture
Yeah,
to
beautiful.
separate.
So what type of mixture does it separate?
Like let's say more dense and less dense mixtures.
Or solid that is not soluble in that solvent.
Yes, sir.
So as it's being spun, those solutes, they want to be thrown away out of the mixture. And that's why they will go and settle at the bottom of the test tube. Is that okay?
Yes, sir.
So the same thing as the earth is rotating. The material at the equator, they want to be thrown away. Why? Because at the equator here is farther from the center. So the closer you are to the center of the earth, the lower will be the centrifugal acceleration. The farther you are away from the center of the earth, you know, since you are far away from the center of the earth, the force of attraction on anybody who's farther away will be less. So the force that want to throw it away will be more on it. So centrifugal acceleration will now cause gravitational attraction to reduce. Thus, the further you are from the rotation axis, the greater the centrifugal acceleration is. So centrifugal acceleration is less, make G to be less at the equator, and it had no effect at the pole. Can anybody explain why that is so? Why centrifugal acceleration causes reduction of acceleration due to gravity at the equator, but at the pole, it does not cause a reduction. No effect. Can anybody tell us why?
Okay. So as
Your
the
name is
as the
what?
earth is Michael,
Your
Michael.
name is what?
Because the
Michael, okay.
radius at the equator
My
is compared to that of the pole, sir.
okay.
It's generally that I was speaking before, sir.
Oh, sorry. I said as the earth is
Michael,
rotating,
continue.
the
Yes.
centrifugal force is pulling the earth apart. Is wants to throw the earth away, which is causing the earth to bulge, and that will increase the radius at the pole at the equator and reduce it at the
No,
pole, which will
radius
now
is
cause
increased
the
by virtue of
gravity
the shape of the earth.
to
Hello, Michael.
centrifugal force will reduce the gravitational attraction. The bigger the centrifugal force, the smaller the gravitational attraction.
So now, before I ask my question again, when you want to rotate as you are, you want to be spinning yourself. If you look at those people that are doing gymnastics, you see that when they want to be rotating, they normally out wide their arms. Is that not
Sir.
on their feet? You see that they will spread out their arms. Is that not so?
Yeah.
Why do you think they are doing that?
So that they will slow down.
No, you see them, they are rolling very fast. Why do they throw out, open their arms when they are rotating, they are cycling on a particular spot? It's because of balance. Do you agree with that?
Yes, sir.
So you can see the earth is also throwing out its arms. That is why at the equator it budges. And because it throws out its arm, the centripetal acceleration is greater, centrifugal force is greater. And that is the meaning of centrifugal acceleration as Ademide. Why is it that it has no effect at the pole? Why is it that centrifugal acceleration has no effect at the pole?
Because the pole is closer to the center of the earth.
Because even the pole directly is closer to the center of the earth, or is almost at the center of the earth. Beautiful. So we move. So this is all that we have been explaining. The shape of the earth, depending on if you want to do calculations, and you want a formula with which you can calculate the earth, calculate the volume of the earth and what have you, you can assume that the earth is a sphere. But in actual fact, the earth is spherical. And the radius is approximately 6,371. This is what a sphere look like, and this is what a spheroid look like. So, I now want to tell you about the meaning of the different shapes of the earth. One, the shape of the earth is a consequence of a balance between gravitational and centrifugal forces, causing a flattening to form an oblate spheroid. Initially a sphere, but the interaction between the gravitational and centrifugal forces causing a flattening to form, causes a flattening at the poles and bulge at the equator. So the shape that is so formed is called an oblate spheroid. It's called an oblate spheroid, which is mathematically in mathematics. Oblate spheroid is referred to as ellipse of rotation. Don't forget, we started with a sphere. If the earth is not rotating, the perfect shape of the earth will have been a perfect sphere. But because its earth is rotating, the balance between the gravitational attraction and the centrifugal forces causes the flattening of the earth at the pole and bulging at the equator. And the shape so formed is called an oblate spheroid. Mathematically, an oblate spheroid. It is further helpful to define a hypothetical gravitational surface called the geoid. What is the geoid? So this is the oblate spheroid. Oblate spheroid, you will see that the equatorial radius is longer than the polar radius. In the sphere, the radius is the same all around. So there is another shape that is called geoid, and it is a hypothetical shape. The shape of the surface that the ocean will form if left undisturbed by wind, tides, and what have you. You know, the wind constantly disturb the wind, the tide, and what have you. Constantly disturb the surface of the ocean. Assuming there is no disturbance at all in any way for the ocean, the shape that the surface of the ocean will have projected into the earth is referred to as geoid. So irregular mass distribution in the earth, we'll talk about that one later. So gravity measurement. There are two types of gravity measurement that are done. The objective of exploration work in geophysics is to associate variation in density or in gravity with differences in the distribution of densities and hence rock type. What geophysics is all about, gravity method in geophysics is all about that. When I measure variation in gravity, I should be able to associate it with variation in density. The variation in density should be in turn associated with variation in the rock types. That is it. Measure gravity variation, relate gravity variation to density variations, and the density variation to different rock types. Occasionally, the whole gravitational field is measured or derivatives. So there are two ways to measure gravity in geophysics. It's either you are measuring absolute gravity or you are measuring relative gravity. If you are measuring absolute gravity, it means you are measuring acceleration due to gravity. In absolute terms, you are measuring the value of gravity from that particular point on the surface down to the core of the earth. And it is usually measured in the laboratory. Like that. It requires very careful experimental procedure. It is very tedious to measure absolute gravity. That is the value of gravity. You measure the gravitational response from the surface of the earth down to the core of the earth. And there are two methods to do that in the laboratory. The two methods of measurement are used. One is the falling body method, and the other one is the swinging pendulum, which we are going to talk about. A network of gravity stations has been established worldwide, that is, gravity stations where absolute value of gravity has been determined. So the network is referred to as International Gravity Standardization Net 1971. That is what is called IGSN 71. Those are the locations on the surface of the earth where the absolute value of gravity are. So it is possible. So we talk about it. We talk about this one later. However, it is much easier to measure relative variation in gravity that is of interest in. So instead of staying in a particular point and measuring absolute value of gravity, there is another way we talk about absolute. In relative, you just measure what is the difference between these two locations. It just tell you that if this location is 20, you go to another location, it tells you that it's 30. What is just telling you 20 and 30 are not the absolute value. It's just telling you that there is difference of 10 between those two locations. That is relative gravity measurement. So let's look at the two methods that we can use to determine absolute gravity. We said the first one is weight drop. You allow this body to drop from a height at time t is 0, and the velocity, because it is stationary, maybe at the top of a building like this. We have Demilade to go up there. Michael will be down here. You say, Demilade, allow the ball to drop. Where Demilade is here, at time t 0, the velocity of the object, because it's stationary, is 0. It will now fall through the distance denoted by z. So at time t, it will reach the surface of the earth, or it will reach a particular point where the velocity is equal to velocity vt, which is velocity at time t. So what you now do is that, since you know this z is equal to half gt squared. Hello, which equation are we using here? Which equation are we using here? Madam, I will call you back.
Of motion.
It's an equation of motion.
Yes, which equation of motion?
The third one.
Beautiful.
UT.
The third one, which says that what? S is equal to
U-
UT plus half AT square.
Yes, sir.
Yes, sir.
That's S. So the reason why UT is not here is because at T is equal to 0, V will be equal to, U will be equal to what? 0. Or T is equal to 0. Is that okay? That's why we
Yes,
are left with half GT square, half AT square. So we are now equating the A to G because the body is falling under the influence of gravity. So if you make G the subject of the formula, in this situation, 2 multiplied by Z. Z is the distance, 50 meters. So divided by T square. In this situation, it took 3.19 seconds. So you can see that you are able to determine acceleration due to gravity at that particular point. So you can do this at any location on the surface of the earth. You have determined the absolute value of gravity. Swinging pendulum, if you use single pendulum, first measured by Pierre Bouguer in 1749. You can guess how many years ago was that? Demilade, where were you in 1749? Or Michael, where were you in 1749?
we're not born, sir.
I say, where were you? I'm not saying you were not born. I say, where were you?
I was even.
Yeah,
11.
okay. So what does heaven look like, Michael? Say you are a citizen of heaven. You don't know. Okay. So it's using pendulum. You remember, you allow the guy to swing. You know the length. Then you know the period of oscillation. That is the time it takes to complete one oscillation. Then you can use this equation, T for the period is equal to 2 pi K, where K is a constant that is related to the pendulum design, and G is the gravitation. This is a constant. These are constant. You know this. Then you can determine G. Simple. Swinging pendulum. So, but if you want to measure relative, those two, swinging pendulum and free fall method, are method of determining, what should I call it now? Method of determining absolute gravity. But to do relative gravity measurement, which is what we often do in geophysics, we use an equipment that is called gravimeter. Gravimeter is the equipment that you use to measure gravity in geophysics. So we have like 2 of these equipment at the department, which we are going to see later on. So this is how it works. How gravimeter works and how relative measurements are done. Gravimeter is essentially a springed instrument that is designed for geophysicists to use to measure variation in gravitational accelerations. So gravimeter are essentially basic, very sensitive spring balances. You can see the spring, and attached to the spring is a load. And you can see the extension already is L. The extension is L. So, if you put a load here, you put an object here that is dense, there will be attraction between the object that is here and this mass. Is that not so?
Yes, sir.
Okay. There will be attraction. So if there is attraction, what will happen to this spring if there is attraction?
The spring will stretch.
we stretch. So the stretch is proportional to the density of the material here. It's directly proportional to the acceleration, gravitational acceleration. Now, this is how, we are talking about relative measurement. Look at the spring at station A. You can see the extension is L1. It gets here, you can see the extension is L2. So it means that material that is here is denser than the material that is here, which causes acceleration to be, you can see the difference is delta L. That is how it works. It means as you move from station 1 to station 2, there is increase in gravity. If you move from here to here, there is decrease in gravity. That is how it works. So a gravimeter measures the length of the spring. The longer the length, the higher the acceleration due to gravity. That is how that one works. So these are typical gravimeter. Look at what they look like. Different gravimeters. That is what they look like. Good. So gravimeters, like I said, from the word gravity meter, you can call them gravity meter. You can call them, they are usually very fragile. Why do you think they are very fragile? Because the spring inside them are very sensitive. If you shake them too much or you handle them roughly, they are prone to drift. They measure discrete data points. Using gravimeter is labor intensive because it requires balancing and leveling. Density variation can be equated to lithology variation, and gravimeter can sense deep into the earth crust. Example of gravimeters are Gulf gravimeters, Lacoste-Rumbach gravimeter, Warding gravimeter, CG5 autograph. Those are examples of gravimeters. And you need to take note in case I ask you in exam. So, like I said, these are examples. At times you can mount them on the back of your bike and take measurements. So we have talked about relative and absolute gravity. The common gravimeter, like I said, the Warding gravimeter, the Sintress gravimeter, the Lacoste-Rumbach gravimeter. Sintress is the manufacturer of the autograph, CG5 autograph. This one is manufactured by Sintress. Lacoste-Rumbach and what have you. So the question we are asking here is, how is gravitational accelerated related to geology? Don't forget that we have said density is defined as mass per unit volume. For example, if we were to calculate the density of a room filled with people, the density will be given by the average number of people per unit space. And we have the unit of per cubic foot. So the higher the number, the more closely spaced are the people. So thus we will say that the room is more densely packed with people. So the unit typically used to describe density of substances are gram per centimeter. So you can see, this is how we define this. You can see this material is tightly packed. Here you have spaces in between them. So this one is denser than this. Again, look at what this guy is carrying. I'm suspecting this is Michael, carrying a lot of load. No feather is less dense. So this is how it works. If this material, D2, the density, you can see this red thing, as they are scattered here, they are not closely packed. So this area is not dense. But here where they are closely packed is denser. So there will be more attraction here. There is what we call density contrast. I don't want to talk about that now. Look at it here. This area that is not dense, you can see the acceleration is small. Acceleration is small. But when it gets here, you can see the extension is longer here, is longer because of the density of material here. the acceleration is lower here. You are using even a falling body method. The guy will accelerate faster here. The ball will accelerate faster here because the material that is here is dense. So you can see because the acceleration due to gravity is high here, you can use it to discover the presence of material that is buried in the subsurface. You can see it will cause an anomaly. So that is a typical CG5 autograph. And I've shown you that measuring gravity is based on Hooke's law. The extension, when the material is dense, the extension will be longer than when the material is not dense. If you look at it here, 3 situations. There is a cave here. Here there is the host rock. Here there is a very dense metallic ore. You can see here that there is a cave. I mean that the material is dense here. You can see the extension is large in the spring gravimeter. Here there is a cave. There is deficit, void of material. So there is no attraction on the gravimeter. You can see the spring shrunk. Here is normal. So you can see where the spring is shorter, we can use it to to detect the presence of cave. And where it expands here, you can see we use it to determine, you can use it to know, okay, there is a dense metallic ore like gold here. Like we have said earlier on, gravity can be used to determine shape of the earth, can be used for hydrocarbon exploration, regional geological studies, isostatic compensation determination, detection of subsurface cavity, location of buried rock valleys, determination of glacial thickness, tidal oscillations, basin geometry. So gravity is important in that we can use it to measure the gravity field of the earth, and we can use it to solve a lot of problems in geophysics. Theoretically, determination of the correct constant in the formula derived theoretically for the normal distribution of the acceleration over the earth's surface. Practically, explanation of the anomaly of the actual gravity field of the earth with respect to theoretical field, you can use it to determine anything that is buried in the subsurface, mineral, oil, even non-artificial material like drums, like piles that are buried. So we can use it, we can use it in investigating deposit of useful minerals, raw materials such as oil, coal, salt, and what have you. We can use it to do a lot of hydrogeology and engineering investigations. So that is that for gravity. We will call it a day and do magnetics at another time. Any questions so far? Any question? Is that Michael?
Yes, sir. What caused the Earth to rotate?
Come again. You said what?
I said, what caused the Earth to rotate?
The earth to rotate. Anybody to answer that question
Yes,
for
sir.
me? Who want to
Okay,
rotate?
sir.
Who want to answer the question for me?
Sir, I'm not sure. I think it's because of the attraction to the star the orbits, the sun, and centrifugal acceleration.
You said what?
The attraction to the sun and centrifugal acceleration causing the Earth to split on its own axis. Rotate on its own axis.
Well, it's something that is very complex, but there are some what should I call it? There are some reasons that has been advanced for it. They said the gravitational interaction between the Earth and other planetary bodies or other celestial bodies and planetary bodies, those interactions, celestial bodies like the moon, the sun, and what have you, they are the one who, for instance, let's assume that there is a body on your right hand side. It draws you, and by the time you turn, the one that is on your left hand draws you. That keeps the earth to be in continuous rotation. Number two is that when the earth was formed, it was through a disturbance, and the disturbance is still, I mean, it's like, how should I put it now? If you bake a bread in the oven, at times you go to where you are buying the bread is still warm, which shows to you that the bread was manufactured in a hot environment. The rotation of the earth was born from the cyclic motion that was in place at the time of accretion of the earth. That is what we know so far about the cause of the rotation of the earth. Question?
Hello, sir.
Yes. What's
So,
your
can we
name?
just
Oh,
Covenant,
you have
sir.
forgotten your name. Eh?
Covenant, sir.
Okay, Covenant, yeah. Assistant class rep. Is the class rep here now?
She's
Okay, what's the name of the class rep?
Ifem, sir.
Okay. Nifemi, where are you? You can see she's not here. Okay, Covenant, ask me your question.
Sorry, sir. Okay, so about the question that Michael asked. So, can we just say
Yes.
gravity is the main cause generally, right?
Yeah, we can. It's not the only. There are 2, 3, 4 different things.
But like
Gravity is sustaining the rotation.
Okay.
You get what I'm saying?
Yes, sir. So, sir,
Yeah.
first question, sir. Okay, sir.
Yeah.
Sir, in your previous slide, there's a particular stuff there, the one that says what's it again? This more mass near the equator. The particular value there, this 9.83 meter per second. Like slide 15, I think.
Is it here?
No, sir. No. Not yet,
Not
sir.
this one.
No. So, like behind. Go back.
Is
Yes,
it
sir.
this one?
Yeah. Yes,
Okay.
sir. There's this G is equals to 9.83, another one 9.87.
Yes. So
So,
the reason is
okay.
because we are saying that at the equator, G is less. You can see this value is less than this.
Yes, sir.
At the equator, G is less. This is at the pole. And the reason why G is less is what we explained here. The bulge, the equatorial radius is longer than the polar radius. There is more mass at the equator than at the pole. And then the centrifugal acceleration.
Okay, sir.
Question. Ask me question, please. So, because when my time to ask question comes, so that you can answer me very well. Ask me any question you want to ask me. So, is it possible for us to have another class tomorrow?
Hello, sir.
I'm listening. Is it possible for us to have another online class tomorrow?
Yes, sir. Around this afternoon period, around 1 to 2, but we have to consult the course rep for that. But we'll get back to you, sir.
So and get back to me. So next
Yes,
week, when we have another class tomorrow, which will be how should I put it, online again. So whether next week or week before the exam, you will have read your material very well, and you will now arrange a physical class in which you are going to bombard me with any question you want. Is that okay?
Yeah.
So tomorrow we do another class. You let me know the time. Then after that, I think tomorrow we should be able to finish magnetics. Those are the two classes. Then after you have read your material very well, we now arrange for a physical class. You will have read your material, and any question you have from one slide to the other, write them down in a paper. Write your question down in a paper, and then we now arrange for a physical class in which we are going to sit down, and you are going to ask me any question whatsoever. Is that okay?
Sir. Yes, sir.
Is that okay?
Yes, sir.
Good. So thank you. Any other question before I end the?
Yes, sir. The attendance.
Yeah.
Shall I send that to you?
I don't need the attendance.
Okay, sir.
You will see that anybody who did not attend this class, there are a lot of questions I will ask that he cannot answer.
That's true. Sorry,
Despite
sir.
the fact that
Sorry. Is there a way that we can get the video, because we have a YouTube video? We always upload our departmental
yes,
video. Can we get this video link?
I will send the video. I will send the recording to you.
Thank you very much, sir.
Yeah. Thank you.
But
You said what?
so
Are you talking to me?
Oh,
I'm
no,
not
no.
giving my matric number. Yes, sir.